A uniform electric field is given by 4.00 newtons per coulomb for its x component and 3.00 newtons per coulomb for its y component. What is the potential difference in moving between points? One point on the x-axis at 4.00 centimeters and the other point on the y-axis at 4.00 centimeters. To solve this problem, let's acknowledge what we need to do and what we need to have to evaluate the potential difference between 2 points. To find the potential difference between 2 points A and B, we know that it is equal to the negative of the line integral from point A to point B of our electric field. We are given the electric field has components of 4.00 newtons per coulomb along the x-axis and 3.00 newtons per coulomb along the y-axis. We're also given that we want to find the potential difference between points A and B, and point A was given as 4.00 centimeters along the x-axis, and point B was given as 4.00 centimeters along the y-axis. We have enough information right here to dive into our calculation. However, I think it's good practice for us to sketch the scenario before we start solving. So let's go ahead with our sketch. So along the y-axis, which will be vertical, we will have the y component in units of centimeters, and I'll also superimpose the y component of the electric field with units of newtons per coulomb. And that way I can plot both the position and the electric field on the same coordinate system. The horizontal axis will refer to the x-axis, and so the x-axis will refer to the x component of our coordinate system, but we'll also have the x-axis refer to the x component of our electric field. Let's do a nice consistent set of units on each axis. I know we're going to go out to 4 centimeters on the x-axis. I'll just go ahead and indicate the same on the negative x-axis, even though I know we're not going there. I know we are also going to a point of 4.00 centimeters on the y-axis. So let me indicate those points. This point I will call point B, and this point over here I'll call point A. To add the electric field, let's begin with the electric field at the origin. The electric field is a uniform field, and we know it has an x component of 4 newtons per coulomb and a y component of 3 newtons per coulomb. That would put us right about here for the electric field at the origin. Being a uniform electric field, I'm going to go ahead and extend this to indicate an electric field line. And at this point with the electric field, now that I have its orientation, the spacing is going to be purely for qualitative reasons. I'm not trying to be 100% accurate with the sketch of my electric field. It is here just to give us a qualitative representation of the problem. So here is our uniform electric field, the points in space surrounding points A and B. Now the problem asks us to find the potential difference between points A and B. It doesn't tell us how we go from point A to B. A line integral, remember, is an integral of a vector field along a particular path. Think of the path as a path that you're traveling on or a path that you're walking on. We're trying to get from point A to point B, and we're not told how to get there. So we can take a number of different paths. We could take a path here going from A to B. I'll indicate the direction we're walking with an arrow on the path. We could take another path, a meandering path, if you will, from point A to B. Those two paths, if we knew what the vector function describing those curves were, we could apply that into our potential difference equation and end up solving for the potential difference between the 2 points, either on that first path, which I'll just call path 1, or the second path, which I'll call path 2. It doesn't matter which path you take for potential difference. The only thing that matters is where you start and where you end. You can get from where you start to where you end by any means necessary. So instead of those meandering paths that we don't know much about, we could maybe choose a path that looks like this, a straight line between points A and B. Let's call this path path 3. We could integrate along path 3. We can also choose another path, just as an alternative for discussion, going along the negative x-axis. I'll call that 4, followed by going along the positive y-axis. I will call that path 5. So we could get from A to B by going along path 4 and then going along path 5. We have all of these alternatives, all of these options at our disposal. What I'd like for us to choose is just the most direct path. Just as an exercise, let's choose path 3 to evaluate the potential difference for, and then let's choose paths 4 to 5 to evaluate the potential difference. And let's see what we get. Let's compare our results. So we're going to have two options. So option 1 is go along path 3. So I'll just say path 3. Option 2 is to first take path 4, followed by path 5. In order to determine the line integral, we're going to need an expression for the differential. Now, the differential comes from our general expression for the position vector. The position vector r is equal to an xi hat plus yj hat plus zk hat. So essentially, our components x, y, and z are functions. When we differentiate this to get the differential, we get dr vector is equal to the differential in x plus the differential in y plus the differential in z. Since we are in the xy plane, dz ends up being 0. So for this problem, our differential for our r is given as dxi hat plus dyj hat. For our electric field has components which I'll just call exi hat plus eyj hat because I like to solve things in terms of variables, where I am defining the x component of the electric field being 4.00 newtons per coulomb and the y component of the electric field being 3.00 newtons per coulomb. Now that we have the expressions that we need for our differential imposition and our electric field, let's apply that to the dot product between the two. We're going to need to evaluate the dot product between the electric field and the position differential. The dot product is just going to be the sums of the products of the components of the two vectors. So we have the x component of the electric field, dx, and the y component of the electric field, dy. This means that the potential difference between the 2 points A and B, as we go from A to B, is equal to evaluating the integral of dEx dx and Ey, the y component of the electric field, dy. Well, this then is just the integral from some initial value of x to some final value of x, the x component of the electric field dx, plus the integral from some initial value of y to a final value of y, the y component of the electric field dy. This right here is going to be the general formula that we are going to use to find the electric field, whether we are going along path 3 or if we take path 4 followed by 5. I chose to express it like this because I recognized that the electric field was given as a unit vector, and I also knew how to express the position differential in terms of a unit vector. So that means that we could evaluate the potential difference by evaluating this integral. And I see that I forgot something. I forgot a minus sign because the potential difference between 2 points is equal to minus the line integral of the electric field. So that means there should be a minus here and a minus here. And I need to go back and put a minus sign. Okay, I do have the minus sign up here on this page. So yes, I'm glad I caught that because it's very important to recognize that the electric field points in the direction of steepest decline of electric potential. And that means there's a negative sign in front of these. Let's start with path 3. For path 3, let's identify what x naught, x, y naught, and y are. X naught is our value at point A. That is 4.00 centimeters, which is also 4.00 times 10 to the minus 2 meters. Our final position along the x-axis for path 3 is x equals 0 centimeters. Our initial position for y is 0 centimeters. And our final position for y is 4.00 centimeters, which is also 4.00 times 10 to the minus 2 meters. Since I see that x naught and y are the same quantities, I'm just going to introduce another constant. Let's just call this constant d, so I can minimize the number of variables I use. So the potential difference from A to B is equal to minus our initial position along the x-axis to 0, our x component dx, minus 0 to our final position on the y-axis, our y component of the electric field, dy. The potential difference then is equal to minus the x component of the electric field, which I will pull outside of the integral because it's a constant, and then minus the y component of the electric field times the integral from 0 to d dy, in which the y component is also a constant, so I pulled that outside of the integral. This means that the potential difference is the product of the x component times x, evaluated from d to 0, and then this is minus the y component of the electric field times y, evaluated from 0 to d. This then is the product of the x component of the electric field times the quantity 0 minus d, minus the y component of the electric field times the quantity d minus 0. This is now the x component of the electric field times d minus the y component of the electric field times d, or for our final algebraic expression, the potential difference is equal to d times the difference between the x component of the electric field and the y component of the electric field. We now have taken this as far as we can go algebraically, so let's go ahead and plug in numbers. The potential difference from A to B is equal to d. D we define to be 4 centimeters, which is 4 times 10 to the minus 2 meters, times the quantity, well, this is the x component of the electric field, which is 4.00 newtons per coulomb, minus the y component of the electric field, which is 3.00 newtons per coulomb. When I plug this into my calculator, I get that the potential difference from point A to point B is equal to 4.00 times 10 to the minus 2 Newton meters per coulomb. But remember, a Newton meter per coulomb is the same thing as a joule per coulomb. And 1 joule per coulomb is the same thing as a volt. So the potential difference from point A to point B is equal to 4.00 times 10 to the minus 2 volts. So let's take path 4 followed by path 5. For path 4, the initial value of x and y, the point we start at, is d0. Where we end is at the origin. For path 5, we start at the origin, and we end up at the point 0d on the y-axis. So the potential difference from A to B is found by summing the line integral along path 4, which I'll just indicate this with a subscript 4 for path 4, of the electric field, and minus the line integral along path 5 of the electric field. Let's evaluate the integral along path 4 first, followed by the integral along path 5. The integral along path 4 is from x naught to x, ex dx, plus y naught to y, ey dy. But for path 4, we're calling x not equal to d and x equals to 0. And we're calling y not equal to 0 and y also equal to 0. Oh, this is easy because there is no displacement along the y-axis, so the dy integral goes away. We already know from previously that the integral of the electric field with respect to x, since the electric field is constant, is going to be equal to E sub x, the x component of the electric field, x evaluated from d to 0. Along path 4, the line integral of the electric field then is equivalent to the x component of the electric field times the quantity 0 minus d, which is equal to minus the x component of the electric field, d. So this is the integral along path 4. Let's do the integral along path 5 now. So the line integral of the electric field along path 5, it's similar to what we had before. It is going to be the integral with respect to x of the electric field plus the integral with respect to y of the y component of the electric field. Along path 5, the displacement in x is 0. So this term goes away. And we should also acknowledge that along path 5, our initial y coordinate is 0, and our final y coordinate is d. So this means that the integral along path 5 of the electric field dotted with the displacement is equal to E sub y, the y component of the electric field, times y evaluated from 0 to d, which is just equal to the y component of the electric field, d. Now we have the integral along path 4 and the integral along path 5. We can now evaluate the potential difference from A to B along that path. So the potential difference from A to B is equal to minus the integral along path 4 and minus the integral along path 5. This is then minus A minus the x component of the electric field, d, and minus the y component of the electric field, d. We can factor a d from both terms, and we're left with d times the x component of the electric field minus the y component of the electric field. And this is the potential difference from point A to point B. Well, let's compare this with what we did previously. So we are comparing the potential difference from A to B from path 4 and 5 to the potential difference from A to B from path 3. Well, let's look at it for path 3. Here is the expression that we get for the potential difference from path 3. Let's copy this and put it on our other page so we can compare. Notice we get the exact same result. It didn't matter that we took path 3 or path 4 and 5. The only thing that matters when we're evaluating the difference in potential between 2 points is where we start, where we end, and the relationship between the electric field and the displacement. How you get from one point to the other point doesn't matter.